Now, material damage models. We have 4 main material damage models. 4-point bending beam test is the one that you use to calibrate material damage models. Low number, repeated load permanent deformation is the one that you use for calibration of rutting models. Resilient modulus type data, you need to use calibration of the resilient modulus data. And indirect tensile strength data is useful, but it's really not sufficient. I will tell you about that later to calibrate the model. All right, so if you look at the calibration settings, let's say for asphalt fatigue, I'm just only focusing on a portion of the fatigue. You can see beta 1, beta 2, and beta 3 numbers that are shown. These numbers are 1, 1, 1, means that uncalibrated condition. The material is not calibrated yet. These are the national values. These are the values that we used in our Excel sheet this morning to calculate NF. Okay, these are the values that we use to calculate NF. So what does that mean? What is the meaning of all these? So let's talk about that in a minute. So when you run this beam fatigue test, here, this is the type of data you get first. Beam fatigue test, 4-point bending beam. Essentially, there are 4 points. You just, flex up and down and up and down. So you calculate the modulus at the beginning of the test. So, it's some number, in this case, 1300 megapascals. And then as the cycles grow, you can see, as the cycles grow, this modulus keeps going down. As the cycles go up, micro cracking in the structure of the HMA starts to grow, and at some point the sample breaks and fails. So typically in the AASHTO guide for this test, AASHTO specification for this test, 50% reduction in initial stiffness is counted as number of cycles to failure. So that is the number of cycles to failure for this test. Let's say this is one of the data. At 10 hertz, by the way, we run this as only one frequency, but we run at different temperatures. At 250 microstrain, at temperature of 20 degrees Celsius. This is the one test. Now what we do is, that was this test. We plot NF, number of cycles to failure, as a function of the microstrain that we apply. This is a strain control test. The device keeps flexing and flexing the beam such that the microstrain is 250 microstrain for this particle test. You repeat the test at a different microstrain, a higher microstrain. So we go from 250 to 300, flex more. And then you have less number of cycles to failure because you are really flexing more. So you're going to break it faster. And the third one is number of cycles to failure at a higher strain level. So what we do is we draw a best fit line to these three, and then we come up with an equation for this. So equation for this is NF, number of cycles to failure, is equal to K1 times 1 over K, to the power K2. This is in logarithmic scale, so this is log scale. So if you take the log NF will be log K plus this times K. So it's actually a linear equation. This is the temperature at 20 degrees Celsius. Now, if you repeat the test at a different temperature, let's say at 10 degrees Celsius, lower temperature, your NFs will go down. So at lower temperature, material is going to break faster. Now, and then the curves will look very similar in terms of they'll be close to parallel. And then if you look at this temperature, the initial modulus for this temperature was, let's say, for the sake of argument, 500,000 psi. Let's say initial modulus for this temperature was 900 psi before we started breaking the sample. So what we do is, in order to consider this shift in the curve down, we use the modulus, 1 over e to the power k3. So if you use a 500,000 here for a 7k, you will get this line. If you use 900,000 here, you would get this line. This is where this equation, NF equation that we use in the morning come from. Is this clear? What's that?
What's the shift factor?
Shift factor is nothing but this 1 over e to the power k2. The shift is because of we are running the test at a different temperature. At a different temperature, there's no shift factor here. That A of t, there's no, but this shift from here to here, the fact that we have lower number of cycles to failure is because we are running the test at 10 degrees Celsius. At the lower temperature, its mixture is more brittle. It fails faster. That's why you have lower NF. It fails quickly. Okay. So upper left, yeah.
Situation where you have a third set of data.
If you run another third set of data at let's say a higher temperature, you can still, and we do that actually, you can still calibrate the same model, because this, for the third set of data, 1 over e, for e will be different. So e essentially is your another input. So this is x, and this is y, and this is z. We are really looking at surface, but from the bottom. There's a surface, we're looking from the bottom. That's how we need to think about. So this is actually an equation for a surface. So two inputs, x and y, and NF is the z kind of a thing. That's how they came up with. And this is really a type of equation in shell model uses also. Now let's move on. So this is the equation, but now these, let's say what happened is during the development of NCHRP, there were a whole bunch of tests run, and an average value of this Ks, and like an average value of Ks come up with for the national purposes, but you are supposed to be checking whether these values are good for the mixtures that are used in your state. Okay, so that's where these beta factors come from. So beta is normally beta 1, 2, and 3 are 1 default, but by just changing the beta values, you're just changing essentially the constant here.
Could you just change the K value?
Yeah, you can. Same thing, but it is better not to do that, so that you have a reference value and you know by multiplying beta how much deviation.
I just find it interesting they allow you to change that in the software, either one.
It shouldn't be. I mean, why? The point is, you're right. Why?
Yeah.
Maybe they thought, okay, they will have a default value for the state, and individuals, if they want to deviate for different locations, maybe. Okay. So this is an example that we can. I have an example here for real data on how to calculate this beta 1, beta 2, and beta 3. Now in here, what we have is I have a spreadsheet. This is actually relatively easy to get if you know the data, beam fatigue data. So yeah, I had number of cycles to failure at 2 temperatures and 2 strain levels. That's written here, and I really use solver to find this beta 1, beta 2, and beta 3 to find this. I'm not going to spend too much time on this. Okay, I'll let you. So I'll not take 5-minute break if you don't mind. 5-minute restroom break. It's a little bit earlier, but there's a reason for it. Do you want me to reveal the reason, or? Okay. Okay. Now we were talking about the Excel sheet that I had to come up with this factors: beta 1, beta 2, and beta 3. As I said, this is a simple Excel sheet. So I have like 3 replicates or 2 replicates of beam fatigue data at different microstrain levels. These are the beam IDs. The first replicate is this. The second replicate here. The difference between these two are the temperatures. This was run at 10 degrees Celsius. This was run at 20 degrees Celsius. And 10 degrees Celsius, 20 degrees Celsius. So we get an average of different replicates, and then you have all these data. And then you come up with NF from this equation, which are these numbers. So K1 times beta 1 here times 1 over E of t. U of t is this value to the power beta 2 times K2. And that's this. And 1 over E, the moduli are the initial modulus values measured at the test, initial modulus, times beta 3 times K3. So when we run a solver to minimize the difference between NF from this equation to the NF actually measured, this difference, we do not vary the K1, K2, K3. We only vary beta 1, beta 2, and beta 3. We just keep these constant so that we know relative to the national values how far our sample is. So it's, in this case, it's slightly different in terms of beta 1 and different, you see all this. Yes?
How do you decide the different test temperatures? Is that somewhat of a standardized thing? Even not same intervals as like the binder test?
This is a fatigue test. So fatigue test doesn't, you don't need to run at very high temperatures or very low temperatures, because fatigue happens at intermediate temperatures. So anywhere between 10 degrees to, I would say, 30 degrees Celsius. And, how did I decide 10 and 20? Based on gut feeling. Really, there's no, so we're just trying to come up with a relationship.
No standard for that.
No standard for
So
that.
maybe if someone's in Florida, they're going to test at higher temperature.
Yes, like 20 and 25, or maybe it's different at higher temperatures.
So along those lines on the creep compliance, I noticed on the temperatures in that were like
Very low.
they were 18 degrees difference.
Yeah.
Again, no significance to that. I mean, who decides?
That particular one does have a standard, AASHTO standard, and it clearly says at minus 10, minus 20, minus 10, and 0 degrees Celsius. So 10 degrees Celsius difference. There's an AASHTO standard that you have to follow to come up with the creep compliance.
Minus 4, 14, and 32. It's 18 degrees apart.
That's Fahrenheit. Yeah. So it's 10 degrees Celsius Fahrenheit difference. So every 10 degrees. And the strength is at minus 10 degrees Celsius.
That's the one that's a curveball there. Everything's Celsius, right?
Yeah. So, yeah, I mean, in super PAVE also everything is Celsius. Here, even though PAVE comes in Celsius, well, in SI units and English units, but all right.